Namaste. In this session, we will study how to use LSTM models for generating text. It is a very interesting exercise where we will be training LSTM on the text written by Shakespeare character by character. So, we are going to use the data set from Andrej Karpathy's writing of unreasonable effectiveness of recurrent neural networks. The problem that we are going to solve is, given a bunch of characters, what is the most likely next character. For example, if we give sequence of character, the model has to predict what is the next character. So, in this case, if model predicts E as the next character, we will have Shakespeare word completed. We can generate longer sequences by calling the model repeatedly. So, just to give you an idea, this is the sample output of the model trained for 30 epochs. We started the model with letter Q and model went on. While some of the sentences are grammatical, most do not make sense. The model has not learned the meaning of words, but consider the model is character based. When training started, the model did not know how to spell an English word or that word were even a unit of text. So, given this background, this is really an impressive performance. A play, you can see that the structure of the output is very similar to the structure of the play. Here the blocks generally begin with a speaker name in all capital letters, followed by the dialogues. So, this is very similar to what you see in the Shakespeare plays, and the model is trained on a small batch of text, 100 characters each, and is able to still generate longer sequence of text with coherent structure. So, just to give you an idea, here we are using the following RNN architecture. So, we are starting the model with a single letter Q and you are asking model to generate the next letter. The model is generating output, the output is the next letter and that letter is again fed into the second node which is generating the next letter and that letter is fed into the next node and so on. So, this is how we get the text generated from RNN. So, here we are giving a single input. So, this is one to many model architecture that we are using here. There are very interesting questions about how do we prepare training data for this, which we will explore during the course of this session. Let us import TensorFlow and other libraries. Make sure you are using TensorFlow 2.0 for this example. We will download the Shakespeare data set. We can look at the text. You can see that there are about 1.1 million characters in the data set. So, length of the text is about 1.1 million characters. We can look at first 250 characters with this particular access mechanism. So, you can see that these are first 250 characters. So, the number of unique characters in the file are 65. So, our job is to predict one of these 65 characters for a given sequence of characters, and the predicted character is the most likely character to be following in the sequence. So, as we studied earlier, we cannot process the string as it is. So, you have to convert string into a numeric representation. So, we use embeddings for converting text into numeric representation. So, here we are defining few helper functions to assign a unique ID to each of the character. So, you can see that the first 13 characters are now mapped to their integer representation. So, the prediction task here is, given a character or a sequence of character, what is the most probable next character? This is the task we are training the model to perform. The input to the model will be a sequence of character, and we train the model to predict the output, and the output is going to be the following character at each time step. Since RNNs maintain an internal state that depends on the previously seen element, given all the characters computed until this moment, what is the next character? So, let us try to understand how to create training data for this task. So, we divide the text into example sequences. Each input sequence will contain sequence underscore length number of characters from the text. For each input sequence, the corresponding target contains the same length of text, except it is shifted by one character to the right. So, what we do is we break the text into chunks of sequence underscore length plus 1 characters. For example, if the sequence length is 4 and our text is hello, the input sequence would be hell, HELL, and the target will be hello. So, let me demonstrate this in here. So, let us say we have word hello and our sequence length is equal to 4. So, what we do is we take a chunk of sequence length plus 1 letters. So, hello is exactly 5 words. So, we take hello and we construct the training data which has got first 4 characters HELL, and for H we expect the model to predict E, for L we want to predict L, for E we want to predict L, this L we want to predict next L, and this L we want to predict O. So, for input HELL we want to predict this particular output. So, thus for the input sequence hell, the target sequence is hello, which is just shifted by one character to the right. So, to do this, first we use tf.data.dataset.from underscore tensor underscore slice function. We convert text vector into a stream of character indices. And then we use indexed to character mapping to obtain the character corresponding to each index. So, you can see that first 5 characters are first here. So, the batch method lets us easily convert these individual characters to sequence of desired size. So, you simply call the batch method, provide the length which is sequence 10 plus 1. So, let us run this. So, these are first 5 sequences, each with 100 characters. So, now what we will do is, for each sequence we will duplicate it and shift it to form the input and the target text by using the map method to apply a simple function to each batch. So, what we want to do is, we want to take this sentence and we want to shift it by one letter, and we want to apply this particular transformation to each and every example in the data set. So, for that we use the map method. So, on the sequences we use the map method and we call split underscore input underscore target function. All that it does is, it shifts it by 1. So, you can see that we use in the input text we have everything but the last character, and target text starts from the second character onwards. Let us print the first example of input and target value. So, you can see that this is the first example where you have a sentence and the target is copy of the same sentence, except that the first character is missing and one character has gotten added at the end of the sequence. So, hope this is clear to you how to construct training data and use it. Let us cut it from hope. Please make sure that you understand the training data construction process. So, each index of these vectors are processed as one time step. For the input at time step 0, the model receives the index of f and tries to predict the index of I as the next character. At the next time step, it does the same thing, but RNN considers the previous step context in addition to the current input character. So, you can see that for letter F you want to predict I. So, we give the index of F as input and it is expected to produce the index of I as an output. Given index of I as an input, is expected to predict index of R as an output, and so on. So, let us create training batches. So far we used tf.data to split the text into manageable sequences, but before feeding this data into the model, we need to shuffle the data and pack it into the batches. We use the batch size of 64. We use buffer size of 10,000 for shuffling. So, we shuffle the data set and then we batch it. Note that we are setting drop underscore remainder is equal to true, and this will essentially drop any of the elements that are left in the last batch. So, look at the shape of the data set. So, it is a tuple each with 64 by 100 dimension. So, these are essentially training and the test sequences. Let me repeat this. So, these are essentially the input and the target sequences. Let us build LSTM model for solving the problem. Here we use tf.keras.sequential model, which has got 3 layers. The first layer is an embedding layer which maps each character to a vector of embedding dimensions. In this case, we have used LSTM with a fixed number of units. We have said return sequence is equal to true, that means we want output from each node, and we have also said stateful is equal to true. Stateful essentially passes the output of the last character in the batch to the first character in the next batch. We are using a specific recurrent initializer called glorot_uniform. We pass the output of LSTM through a dense layer containing number of units equal to the vocabulary size. We are doing this because we want to predict one of the 65 characters, which is the size of the vocabulary in this context. So, this is a function for building the model. Let us build a model. For each character, model looks up the embedding, runs LSTM runs the LSTM one time step with the embedding as input and applies dense layer to generate the next character. Let us try the model. Let us check the shape of the output. So, in this case you can see that we have a 3D tensor here which shapes 64 by 100 by 65. Here 64 is the batch size, 100 is the sequence length, and 65 is the size of vocabulary. In the above example, the sequence length of the input is 100, but the model can be run on inputs of any length. Let us look at the summary of the model. We can see that the model has 5.3 million parameters, a very large number of parameters indeed. To get the actual prediction from the model, we need samples from the output distribution to get the actual character indices. This distribution is defined by logits over the character vocabulary. Note that it is important to sample from this distribution, as taking the argmax of the distribution can easily get the model stuck in a loop. Let us try the model on first example of the batch. So, these are the sampled indices, which is a prediction of the next character index at each time step. Let us decode this to see what model has predicted. Note that we have not trained the model. So, this is still an untrained model. So, you can see that currently the next character prediction is not really working that great. We are getting quite random characters as next character. So, Let us try to train the model and see if we can get better results with the model. So, at this point the problem can be treated as a standard classification problem. Given the previous RNN state and the input this time step, you want to predict the class of the next character. We use sparse categorical cross entropy loss in this case because it is applied across the last dimension of the prediction. Because our model returns logits, we need to set the from underscore logits flag. So, we define a loss function and then calculate the loss So, you can see that the prediction shape is 64 by 100 by 65, where 64 is the batch size, 100 is the sequence length and 65 is the size of the vocabulary, and the scalar loss is 4.17. Let us configure the training procedure using model.compile method. We will use Adam optimizer over here. We will use model checkpoint to ensure that the checkpoints are saved during the training. So, we give the checkpoint directory and provide the checkpoint prefix. Let us train for 10 epochs and note that we are using GPUs here for faster training. Okay, now that our model is trained, let us look at how to generate the text from the model. We will restore the latest checkpoint of the model, and before proceeding, let us check the model summary for sanity. You can see that the model that is restored from the checkpoint is exactly same as the model that we built and the model that we trained a few minutes earlier. Now, let us try to understand how do we generate the text. So, we start by choosing a start string, we initialize the RNN state and we set the number of characters to generate. We get the prediction distribution of the next character using the start string, using the start string and the RNN state. Then we use a categorical distribution to calculate the indexed of predicted character. We use this predefined character as our next input to the model. The RNN state written by the model is fed back into the model, so that it now has more context instead than only one word. After predicting the next word, the modified RNN states are again fed back into the model, which is how it learns as to get more context from the previously predicted words. Looking at the generated text, you will see the model knows when to capitalize, make paragraphs and imitates a Shakespeare like writing vocabulary. With a small number of training epochs, it has not yet learned to form coherent sentences. So, let us look at how to code in Python the same thing. So, we specify the number of characters to generate, we convert our start string to its number. This is the array where we will be storing our result. We specify the temperature value. Low temperature results in more predictable text. If you want more surprising text, we need to set up higher temperatures. Temperatures, we use batch size of 1. We first obtain the prediction from the model, we remove the batch size dimension, we use categorical distribution to predict the word written by the model. We get the prediction ID, we pass the predicted word as the input to the model. So, input eval is get expanded by including the predicted word, and we append the predicted character to the generated text. So, this is how, and we run this in a loop to generate, in this case, about 1000 characters, and finally we return the generated text. So, as a homework exercise, I would suggest you to check out what kind of text is generated starting with Romeo. You can improve the results. If the results are not good, you can improve them by increasing the number of epochs. You can also experiment with a different start string or try another RNN layer to improve the model accuracy. Other way to improve the model accuracy is by setting appropriate temperature parameter. So, wasn't that a fun exercise? I am sure you must have enjoyed seeing machines generate text just like Shakespeare. So, I would encourage you to try more such kind of examples, or try the same example with different training data and see what model outputs. So, LSTMs or in general RNNs are very powerful models, are being used extensively for sequence mining problems. Hope you enjoyed this session with us. See you in the next session. Namaste.